I'm converting the whole chapter heat into the form of question and answer, and this is last part, and this is part number 5. And in part 5 and part 4 is mainly related to numerical problem, and that's why today I'm going to solve numerical problem which is concerned with the chapter heat. Many numerical problems are taken in this class, but maybe they are not in the order. I mean to say, some of them may be simple also, some of them may be a little difficult for the student also. Without caring any order, I am presenting some of the numerical problem here. Look at this. Hot water of mass 10 kg at 90 degrees Celsius is cooled for taking bath by mixing 20 kg of water at 20 degrees Celsius. What is the final temperature of water? Specific capacity of water is given. It is 4200 joule per kg degree Celsius. This is clearly mixing of water. One is hot water, another is cold water, and final temperature of the water will be less than the hot water and more than the cold water. Okay, that's why I want to take two different cases. One is hot water and another is cold water. In case of hot water, mass is given 10 kilogram, and in case of cold water, mass is 20 kg. Initial temperature of hot water is 90 degrees Celsius, but initial temperature of cold water is 20 degrees Celsius. Final temperature we don't know, and this is the question. In both the cases, final temperature we don't know. I mean to say, when hot water and cold water are mixed with each other, then the final temperature will be between the hot and cold. It is less than 90 degrees Celsius and it is more than 20 degrees Celsius. We know this, but what is exactly the value of final temperature we are going to find out. And I want to tell you one more information. It will be better to have M1, S1 and T1 in case of hot water. In case of cold water, M2, S2 and DT2. And 111 is taken in hot water and 222 is taken in cold water for our convenience. Now we have to know that hot water loses heat energy and cold water gains heat energy. And what is the loss of heat energy by hot water? We can calculate by using the formula heat loss equal to M1 into S1 into DT1. But here I am writing only S. The reason is, in both the cases we have same water, that's why specific capacity is same, and so S represents both of them. So in case of cold water also, M2 into S into DT2. S remains same, and DT1 is T1 minus T. T1 is here initial temperature and final temperature is less than T1. Because this is hot water and its initial temperature is 90 degrees Celsius and it is mixed with cold water. Now final temperature will be less than 90 degrees Celsius. That's why difference will be T1 minus final temperature, T1 minus T. But in case of cold water, it is different. Mass is 20 kg. And S remains same, specific capacity in both the cases are same, and T minus T2. T is final temperature, T2 is initial temperature of cold water. Initial temperature of cold water is 20 degrees Celsius. When it is mixed with hot water of 90 degrees Celsius, certainly its temperature rises from 20 degrees Celsius to certain value. That's why final temperature T will be greater than T2. So difference of temperature is T minus T2. We have to take care about this. In case of hot water, T1 minus T. In case of cold water, T minus T2. Next step. Now I am going to write this temperature also. Initial temperature 90 degrees Celsius. Here 90 is written. Here initial temperature is 20 degrees Celsius. That's why 20 is written. T1 and T2 are taken. Now we have to find out T. Now according to the principle of calorimetry, we know that heat lost by hot water is equal to heat gained by cold water. That's why heat lost equal to heat gained according to principle of calorimetry. Now 10 into S into 90 minus T, this is heat lost, is equal to 20 into S into T minus 20. This is heat gained. 20 into S into T minus 20. This is heat gain by cold water. Heat loss equal to heat gain. 90 minus T is taken in left hand side. 10 is taken to right hand side and it divides 20. When 20 is divided by 10, we will have just 2. And then S and S cancel each other. I didn't take the value of S because in both the side we have same S and we can cancel them. And so 2 multiplied by T minus 20 is left towards right hand side. Now next step, 2 into T 2T and 2 into 20 40. Now if this minus T is taken to right hand side, 2T plus T becomes 3T and minus 40 is if taken to left hand side, then 90 plus 40 becomes 130. That's why 3T is equal to 130 and value of T will be 130 by 3 and T is equal to 43.33 degree Celsius. And this is the final temperature. That's why we can write, therefore final temperature is 43.33 degrees Celsius. Okay, let's go to another question. Question number 86. What amount of heat energy should be supplied to increase 15 degrees Celsius temperature of 5 kg silver having specific heat capacity 234 joule per kg degree Celsius? If the same amount of heat is supplied to 5 kg of steel of specific heat capacity 447 joule per kg degree Celsius, then what will be the change in temperature? This second case is related to first case, and in first case what is told, what amount of heat should be supplied to 5 kg of silver to increase its temperature by 15 degrees Celsius? We have to find out the amount of heat supplied to silver first, and then the same heat is if supplied to iron, then what will be the change of temperature is told. That's why we have two distinct cases. One is the case of silver, so I am writing silver first. Change of temperature dt is given 15 degrees Celsius. Mass of silver m is 5 kilogram and specific capacity S is 234 joule per kg degree Celsius. Heat required is question mark. Now we have H equal to m into S into dt, and m is 5 kg into 234 joule per kg degree Celsius into 15 degrees Celsius. Now kg cancel, degree Celsius cancel, and only joule is left, and that's why we'll get this value 17550 joule. This much heat energy is required. Required heat energy for silver is 17,550 joule. Now same heat is if given to 5 kilogram of steel, then what will be the rise in temperature is the question. That's why second case is steel. Now quantity of heat is same, 17,550 joule taken from first case, and mass of steel m is equal to 5 kilogram, specific capacity S equal to 447 joule per kg degree Celsius. Change in temperature dt we are going to find out, and our equation is Q equal to m into S into dt. Here I want to mention something. Look at this. Here I have written H equal to m into S into dt. Here I am writing Q equal to m into S into dt. Both the equation are same. Q is quantity of heat. Here the same is represented by the symbol H. H means heat. Okay, now 17550 in place of Q is equal to mass 5 kilogram, specific capacity 447 into dt. Here I am not taking the units for each of the physical quantity. It is not compulsory to take the units in the process. If you are confused with the unit, then you can avoid this unit in the process. Okay, next step. 5 multiplied by 447 becomes 2235, and if this 2235 divides 17550, then difference of temperature will be 7.85 degrees Celsius approximately, because after decimal point we have taken just 2 digits, other digits are not taken. Therefore change of temperature will be approximately 7.85 degrees Celsius. Let's go to another question. Calculate the amount of heat absorbed by 1.5 kilogram iron when heated from 30 degrees Celsius to 110 degrees Celsius. Specific capacity of iron is given 440 joule per kg degree Celsius. Looking at the question, this is very simple numerical problem. And without confusion, we can write the given mass of iron M 1.5 kilogram, initial temperature T1 equal to 30 degrees Celsius. Have you noticed this? I am always taking T1 as initial temperature, T2 as final temperature. Okay, now next, final temperature T2 equal to 110 degrees Celsius. Specific capacity S is equal to 440 joule per kg degree Celsius. Quantity of heat absorbed Q equal to question mark. We can write H also, heat energy also. Okay, we have Q equal to ms dt and value of M is 1.5 kg and specific capacity 440 and T2 minus T1. I am writing the value of T2 and T1 also, 110 minus 30 degrees Celsius, and kg cancel here, kg and kg is cancelled, and then here degree Celsius if we cancel, then we'll multiply 660 with 80 degrees Celsius, we'll have this result 52,800 joule. Therefore, the amount of heat energy required is 52,800 joule. Okay, now next. Now we are continuously doing some numerical problem. Calculate the rise in temperature when 1 kilogram of water is heated with a heater of 1 kilowatt of heat, 84 kilojoule. Some of the question I have taken from some famous board examination, and the sentence may be a little different than what we are expecting. It doesn't make any difference to us. We have to just solve the numerical problem. Mass of water M is equal to 2 kilogram. Quantity of heat Q equal to 84 kilojoule. Kilojoule means it is 1000 times greater than joule. So we have to convert it into joule because we are following joule in our numerical problem. 84 multiplied by 1000 becomes 84,000 joule. Specific capacity of water is not given, that's why I am taking myself 4200 joule per kg degree Celsius. According to requirement, this can be taken in the numerical problem, and rise in temperature dt is the question. Now our equation is Q equal to M into S into dt, and taking the value we are going to find out dt, and 84,000 divided by 8400, 4200 multiplied by 2 becomes 8400. When we divide this, then we will get 10 degrees Celsius. Therefore rise in temperature is 10 degrees Celsius. Okay, next, if a heater of power 1000 watt gives 4.2 into 10 power 3 kilojoule of heat energy, what will be the temperature raised in the 20 kilogram of water with temperature 30 degrees Celsius by that heat? Specific capacity of water is given here. It is 4200 joule per kg degree Celsius. Looking at this numerical problem, here 1000 watt power is given, but the use of this power is not in the numerical problem. We are writing the power equal to 1000 watt, but we have given heat energy directly, and this much heat energy has to be used in the equation. Power doesn't have any use in this numerical problem. Heat energy Q is equal to 4.2 into 10 to the power 3 kilojoule, and kilojoule has to be converted into joule. 4.2 into 10 to the power 3 should be multiplied with 1000. 1000 means 10 to the power 3. I am multiplying with 1000 to convert it into joule. Same base 10 having power 3 and another 3 plus 3 6, and 4.2 into 10 to the power 6 is the final. Now mass of water M is equal to 20 kilogram. Initial temperature T1 equal to 30 degrees Celsius. Final temperature we are going to find out. Specific capacity of water equal to 4200 joule per kg degree Celsius. We have this equation Q equal to M into S into dt, and Q is 4.2 into 10 to the power 6 equal to M is 20, S is 4200, and we are going to find dt. And 4.2 into 10 to the power 6 is equal to 4200 multiplied by 20 becomes 84,000. Now we have to convert the left hand side into this real number, not in power of 10. 4.2 multiplied by 10 to the power 6 becomes 42 having 50, and if it is divided by 84,000, and then we will get dt, and dt is equal to 50 degrees Celsius. This is the rise of temperature, but final temperature is a little different. Final temperature means the initial temperature plus rise in temperature. So the rise in temperature is dt, and initial temperature is T1. If we add both of them, then we will get the final temperature, that is 80 degrees Celsius. Okay, next. A person heats 20-liter water at 4 degrees Celsius with 2016 kilojoule heat energy. How much temperature will rise of it? Space heat capacity of water equal to 4200 joule per kg degree Celsius. I want to mention again different numerical problem I have taken from some of the famous board examination, and so I am not changing the words and sentence of that question. Now we are going to solve the problem. Volume of water is equal to 20 liter. We are not using this physical quantity in the numerical problem, that's why I am not taking any symbol. Initial temperature T1 is equal to 40 degrees Celsius. Space heat capacity, it is given 4200 joule per kg degree Celsius. Heat required Q is equal to, it is given in kilojoule kg, and that's why we have to multiply it with 1000, and finally we get 2016,000 joule. Now next is final temperature. This is the question. Here we have a little twist. In place of mass, volume of water 20 liter is given. That's why 20 liter of water is of 20 kg mass. This can be mentioned here in this way: mass of 1 liter of water equal to 1 kilogram, and therefore mass of 20 liter of water equal to 20 kilogram. So we have now Q equal to m into S into dt. Now taking the value, we have to find out dt, and dt is equal to how much? It is equal to 24 degrees Celsius. This is simple calculation. Okay, therefore final temperature will be increase of temperature plus initial temperature. Initial temperature is 4 degrees Celsius and rise in temperature is 24 degrees Celsius. That's why final temperature will be 28 degrees Celsius. Now next, 91. An iron ball of 2 kg mass having specific heat capacity 440 joule per kg degree Celsius is cooled from 40 degrees Celsius temperature to 30 degrees Celsius. How much amount of heat is released? It's a very simple question. Okay, we are writing the given information. Mass m equal to 2 kilogram. Specific heat capacity S is equal to 440 joule per kg degree Celsius. Initial temperature T1 equal to 40 degrees Celsius, and it is cooled down to final temperature T2 equal to 30 degrees Celsius. Have you noticed this? I am taking T2 as final, T1 as initial. It doesn't make any difference. Amount of heat S equal to question mark. We have H equal to M into S into dt. M is 2 kg, S is 440 joule per kg degree Celsius. Here instead of writing T2 minus T1, I am writing T1 minus T2 because the difference of temperature, it is cooled down, difference of temperature is 10 degrees Celsius, and this never be negative. So this is the case where instead of writing T2 minus T1, I am writing T1 minus T2 because temperature fell down from 40 degrees Celsius to 30 degrees Celsius. Difference should be 10 degrees Celsius, and it comes only T1 minus T2 if used. Okay, next, 880 joule per degree Celsius, kg cancel, 440 multiplied by 2 becomes this much, and T1 and T2, if we take value 40 degrees Celsius minus 30 degrees Celsius, then we will get 10 degrees Celsius. Again degree Celsius cancel each other, and this is equal to 8800 joule, 8800 joule. That's why, therefore, the amount of heat released is 8800 joule. Now next, calculate the mass of an iron pan which requires 70,800 joule heat to increase its temperature from 40 degrees Celsius to 110 degrees Celsius. Space heat capacity of iron is 470 joule per kg degree Celsius. Okay, this is also simple numerical problem. Quantity of heat Q equal to 70,800 joule. And initial temperature is given 40 degrees Celsius, and final temperature also given 110 degrees Celsius, and space heat capacity is 470 joule per kg degree Celsius. Now mass of iron is equal to what? Now we have Q equal to m into S into dt, and 70,800 joule equal to m into 470 joule per kg degree Celsius into difference of temperature is T2 minus T1, and we are going to find out the mass. Now beside mass everything is given, so we are writing the value again. 110 degree Celsius minus 40 degree Celsius, and degree Celsius cancel, and then mass will be 70,800 divided by 32,900, and our answer will be 2.15 kilogram mass. Therefore mass of iron is 2.15 kilogram approximately is written, because after decimal point I have taken just 2 digit 1 and 5. After that some digit are ignored, so I am writing approximately. Okay, I think I finished this chapter with numerical problem. Now next class we will start some other chapter. I'll convert some other chapter into the form of question answer. Okay, this much for today.